Golubev is a tenured professor of aerospace engineering at Embry-Riddle Aeronautical University, where he has taught since 2001. He is a recognized expert in computational fluid dynamics and unsteady aerodynamics, particularly concerning propulsion and aeroacoustics. He earned his PhD in aerospace and mechanical engineering from the University of Notre Dame. He's the founding director of the Propulsion and Aerodynamics Computational Laboratory at the Daytona Beach campus. And his work centers on high fidelity numerical analysis of flow structure interactions with applications in UAV operations in gas environments, jet propulsion, and urban air mobility noise reduction. He's recipient of a Fulbright U.S. scholarship for alternative wind energy research. He's elected fellow of the Royal Aeronautical Society and an AIAA Associate Fellow. Dr. Golubev has authored nearly 150 referee publications, and he has received research support from major organizations such as NASA, the NSF, and the Air Force Research Laboratory. Thank you so much, Professor, for being with us. The floor is yours.
Thank you all. All right, good early morning. I mean, usually you would never see like this in America. It was later, then you start at 8. We never start before 9 ever.
Okay,
Okay, then and later.
good to know.
But, but at the conference we do it. Okay. Okay, so I hope you know a little bit about Embry-Riddle. It's one of the best aerospace schools. I'll talk about more of this in the future, but we actually compose of both campus, 2 campuses, right? Daytona Beach, well, 3, 2 domestic and 1 online. So it's Daytona Beach is the biggest domestic campus. It's Florida. There's also Prescott, which is Arizona, and then there's Worldwide, which is actually about 60,000 people. So we actually have a huge worldwide campus. And it's actually almost like number 1 in kind of all records, like we're one of the best of the best in online education. But one of the things is that we're present on all Air Force bases, United States Army forces, because all Air Force bases take the classes from their own. It's almost required. All these pilots, etc. And the domestic campus, back to the Daytona, which is the center of all activities. Even the headquarters of all like worldwide, etc. They're all like next door, so we know the same things. But we are composed of engineering college, arts and sciences, which is all physics, chemistry, and everything. Then business, and aviation. I should say that all campuses, all colleges have something to do with aviation. Arts and sciences, all programs, as you will see later, had some flavor of aerospace. So this is what makes it most unique. It's very aerospace focused. Not traditional courses, so not like that. Anyway, so we're located in a very beautiful state of Florida, sunshine state, a lot of sun, but there are hurricanes. Now we're here at Daytona Beach, now take an hour where they launch all the SpaceXs, etc. Just like 30 miles from us or something. So we can see the launches on the beach, especially at night. Beautiful, you can go to the beach and see like fire goes through the skies. Very interesting thing. Miami is here, the next level here, Hawaii is here, so you know what the glory is. So we're surrounded by megapolises, but we're kind of like a small. Well, Daytona Beach, you would say it's composed of maybe like, I don't know, 6, 7, 8 townships. Small, Hollywood Beach, Port Orange, etc. I live in Austin. It's about 20 minutes driving. So, anyways, so that's us. So this is some formalities about the school. It's independent, non-profit, educational university, serving cultural, diverse students seeking various innovation as space groups. Yeah. Okay. I'll just mention that 2 campuses, worldwide. Yeah, that would used to be. It's actually pretty old information. I tell you, I was asking my department chair to give us the best of the best, the latest, but the new department chair is lazy. Sorry. It's the French lady, she doesn't want to do it. So, so for that reason, she just like sent me some kind of like overall, like one number. I'll show you that slide, one single slide. Used to be Tassos, he would be like the whole spreadsheet of different statistics. Not much anymore. Okay. Anyway, created by the Commission of Colleges of Association of Colleges and et cetera, multi. So we have a lot of money coming from the Department of State, Department of Defense. Department of State is tiny, like Fulbright scholarship with Department of State. Get something, but not much, right? Department of Defense, of course, big, respects because we are the largest ROTC contingent in the country, I think. As ROTC is like basically those people who want to serve in the army and take the class at the same time. So we have the largest group of people. You'll see them marching on campus all the time, like raising the flag, etc. So that's pretty cool. And students basically get the education for free if you serve in the army. How about that? Because I know some Russians will knock into the door. Can we actually serve in the army? But I mean, it's not for everyone. But I guess if you're a citizen or maybe even resident, I don't know, you can serve in the army and get education for free. That's another option. Because it's expensive. It doesn't say anywhere in the slides, but the education at this university is really expensive. It's a private school. They call us Harvard of the skies. Not just because it's like Harvard itself, but because of the tuition as much as in Harvard, very expensive. So, and that's the problem. For many, so many students take the loans, or federal loans. US citizens can take the loans, I guess residents too. And then they have to pay the debts. And average debt, I remember 10 years ago, I never thought about it before because, we international students would come for free, right? You would get your undergraduate education somewhere else, like I was in Russia, like people all over the place. Then they come and of course, your education as a master or PhD is free because you get money from the grants, like GTA, graduate teacher assistantship, all kinds of things like that. So don't worry. But the students like going for undergraduate degree have to pay, and they pay huge money. And usually the average debt, that's what my student was telling me. I'm really good shape. I only have like $100,000 to pay back. That's just like nothing. So, but that's what you can expect. So you have to be more careful about that. But then, and that's why we cannot really obtain much of US citizens to go to graduate school, because all they want to do is look at that 90% employed in the first year. They get like several offers right away from big companies. They have huge money. It's not like you get a stipend for PhD. You get like as much as a professor does. Now, especially if you go to businesses like Boeing or Lockheed or something, that's pretty much the same as you would get as a full professor right away. So, I mean, why do you have to wait for like graduate school and like pass and then wait and then just go to the industry? And then actually, by the way, the people in the industries, I know some companies, big companies, and also, of course, if you go to NASA, all this federal Navy building, they also can support your continuing education. So you can get your master's and PhD as you actually work for those industries and federal agencies. So for that reason, I mean, it's not easy to retain students in a great program. Yeah. So that's why we mostly rely on internationals. Right? That's the thing. And, that's actually common pretty much for every university. So it's low. As I mentioned all about our space, we have a fleet of, I don't know, more than 100 planes, I guess, because we have the pilot school used to graduate 30% of all commercial pilots in the US. It was really big. I mean, it was originally a pilot school, right? It was established exactly 100 years ago, 1926. This year is 100 years pilot school. And it's established as a pilot school in Florida, in Miami. And then they moved from Miami like around the 60s. Everyone is just like angry about that still. Because Miami is still kind of a lot more entertaining than Daytona Beach, so let's put it this way. But nevertheless, I mean, that was very free for them, free space to use international airport, Daytona Beach, which is actually that's what they used to use. So we get it at the international airport. So with initial planes. So it's so just briefly, since I need to talk about every like small college, big college, what they do, there's signature research areas, and you can see like even arts and sciences, like again, all kinds of things here. So in terms of research, they can do like a lot of things related to aerospace, like aviation psychology, human factors. These are the guys, for instance, they take care of the psychology of the astronaut when it goes to Mars. So they investigate what happens with the psyche. So they do some kind of experiments. I'm not sure which ones, but they do some research on this thing. In fact, I'll talk about it in a minute. It will be a big surprise for all of you guys. The last project I'll be mentioning here is completely out of the blue. So, but you'll see the relationship to this one. Okay, ergonomics, safety, research methods, astronomy. And by the way, yeah, we have in the physics department, we have a very big program in astronomy and particularly the atmospheric, layers and ionization and everything else. They actually have been historically very big in this. That's one of the focus areas established by some very famous professor for like years and years ago, like 20, 30 years ago. So they got a lot of money from NASA, from NSF, all those things. So that was actually a very focused area in these things. So and they have a huge telescope on top of the building. Actually, so if you look at that building right there, see this thing? It's a telescope. So they actually give the free tours to people on the open days, like you can go there and see all the skies in great detail. You can see all the aliens flying around. So that's latest news that Trump is going to disclose the latest about the aliens. Well, he was just announcing that he got the information, so we also know very soon that the aliens all around us. So that's that was just like yesterday in the news. Just sure. But anyways, good point. So you see all kinds of things. Cosmic rate, very propulsion, atmospheric physics. Atmospheric physics is very good. That's it. In fact, we can go great with them. They're also very good at math. So, of course, mathematics is one of them. But for instance, engineering physics, which is kind of it's strange, but the engineering physics department is located in the College of Arts and Sciences. And for many years, it was the few engineers. Historically, it was happening like that. So they have a very strong engineering college in engineering physics, and we collaborate with them. Because, for instance, they do a lot of nonlinear controls, and we use this nonlinear controls for various purposes. So that's not this anyway. And then one Romanian guys taking care of nonlinear wave phenomenon. So here's this like fighter channel. Have this waves bouncing back and forth. If it looks at nonlinear interactions, that's not a game. Those experiments motivated Professor Ludwig. Okay, configuration. Yeah, that's all the people who do everything to do with the operations. So it includes the maintenance, meteorology, like flight dispatchers, all kinds of things like that. So safety management, runway design. So we have this thing you can go to training. What they do with this huge flight simulation simulators. I tried it. Actually, that's how they teach the students. So those who want to be pilot, you fly those small things like the Cessnas, and then you go to the flight simulators, which actually has flight simulator for Boeing 737 or 787 or Airbus, etc. And you just do the actual real practice before you go to work for these companies, for the airlines, right? Airlines, they need to real experience for their flight simulators. I tried because they can get the open house days. They like allow people to do this. I crashed everything. Right away. It's impossible. I mean, it's very difficult. You have to really be prepared for this thing and then requires practice. I just tried, boom, didn't work. But I mean, so I'm not ready to be like well, anyways. Okay, so college of business, even business, it's all related to aerospace. If you think about it, it's all related to airline operations, airport operations, aircraft finances, leasing, general aviation safety analysis, marketing, everything in terms of business related to aerospace. Okay, or any kind of break like that. So that's and we do break with them as well. In fact, I had a what do you call it? Something to do with the business in terms of the CTR. So we have the programs when you're trying to develop your own company. And you basically use the technology which you develop as part of fundamental grants, NSF, NASA, etc., and to develop this in terms of the real commercialization process, right? So it's basically something which the business people can help with, because they can help with the business plans or something like that. So, for instance, I have some colleagues who actually work with me on those things because we got a grant. Of course, you know that these two guys sitting for the student from my Kinzel. Kinzel gets those CCTI grants all the time. Yeah, and then Juan Pablo. So basically, you need to collaborate. You guys collaborate with business people, like business departments.
We don't talk to that part of it.
So I used to talk. I mean, in fact, it's good for them. I mean, I was told that it's very good to involve financial advisors from business side. So we're involved, but you see, you have more like not involved. So it's a different stage. But I do have a lot of friends there, and we, in fact, there was a joint team between business and engineering when we were trying to put this new technology which we developed for the small UV controlled by synthetic jets. There was no aeros, nothing. It was like all controlled by synthetic jets. And so there was like a poster and some for the venture capitalists. So venture capitalists came, was a whole bunch of presentations from business and engineering like combined. And so there was one guy, I remember his name was Garcia. He said that he's a billionaire. He lives in Miami and he invests in a very high risk things. And he was actually very interested in that one. But then he told me what he's invested in. That was really brilliant. For instance, he was investing heavily in some sort of hypersonic transportation for people to fly from London to Sydney in Australia, like in a couple of hours. And I said, what exactly is like there's some kind of venture, somebody invented this thing, and then he was supporting this with money, the venture capitalist. So basically, it's like a gun. It's like you put it as a rocket, like in a pew, and then you like fly it straight to the Sydney, and finally you're there. And I was always try to envision the businessman after this coming out of this missile, more or less. I think he will not be ready for the QC. But that's just interesting. Oh, it's amazing what kind of things people invest in. So yeah, of course, nothing flies like this. Yes, you can probably do that, but basically, I'm not sure you will survive. Yes. Anyway, so it's interesting. Always interesting to talk with the business people because they some crazy ideas. Yeah. And even here on the trip, I was in Paraguay. I met venture capitalists and British who lives in Paraguay because he doesn't have to pay any taxes. Paraguay is like sanctuary, many people to go there because you're actually very good in that. And he was telling me about some kind of crazy ideas they invest in. All right. Let's now focus more on the College of Engineering. That's our areas, right? So that's what we are. A lot of modeling, simulations, complex one, physics systems. Well, it's scramjet, it's a hypersonic, right? Scramjet, turbulence, acoustic, aircraft, but there's a lot of things: aerodynamics, propulsion, you name it, aerodynamicity. And that's actually only part which relates to aerodynamics and propulsion, which is my area. We have three areas: aerodynamics, propulsion, we have the controls, and we have structures. So people in controls and structure themselves have their own labs, there's a lot of research there. So I can actually make a lot of space structures here, right? But you can see a lot of things here in general, like design, flight test engineering, economy, applied design engineering, cybersecurity is a big thing now. Robotics, yeah, that's the new lady who came to off of my lab. the new chair, I'm from Michigan Aerospace experiments. But yeah, we have now a very powerful experimental thing. I'll show you later on. We have this $10 million investment by the state in the wind tunnel, which we actually built campus. It's one of the biggest. And we have now a bunch of experimental faculty who's doing research. Well, quite, not quite new, well, 10 years. CV, that's my area, but we have several faculty in CV. I'm just director of the lab, but we're about maybe 5-6 people focus on CV in one area now. So that's a big thing. And then let's see what else. Engagement around software. Yeah. Okay, this is our college. Used to be when I came in 2001, that's the most modern building. If you look at the campus at that time, there is nothing to do with current. Everything was demolished except for the building. So this is now the oldest. Everything else is now brand new. So this is like a shiny campus, more or less. Looking that is like very, very modern and necessary. All right. So now what's the split in the engineering departments? Well, this is what makes it really, really. We're like 75% aerospace engineering. And usually it's the opposite. Usually aerospace engineering is either like 30 departments or it's part of the mechanical aerospace or something like that, right? Or mechanical aerospace in ocean something. I've seen this different arrangements, but usually aerospace is 30. We have like majority of things in aerospace. And in fact, there's a filtering process. So after first 2 years, all the students in engineering disciplines take the same courses, so they don't split until they go to the third year. And then the third year, they actually filter. So the best of the best get admitted to the aerospace. The rest, no jobs. So that's how it works. So we are really proven in aerospace. You see all those other places, computer science, electrical, mechanical, civil, regular things. But they also have aerospace flavor. But we like the ones which are focused on all does. So as I mentioned before, the aerospace program, we have the aerospace propulsion, structure, and dynamics control. That's the biggest split. And so we have like subgroups of faculty courses within each discipline or each area. Let's put it this way. So we have our own curriculum committee, like search committee, etc. So for instance, if we need to like find a new faculty in this area, like dynamics propulsion, we like gather this search committee. So it's only like so many faculty in this area. The others don't bother, so they don't do the same structure. So these are a list of courses which people usually take. Now it's more. It's actually again without data information. But for instance, this fall I'll be first time introducing. Well, not introducing myself because there was the course was taught before the dynamics. I'll just actually make it a bit more of aerodynamics and acoustics. So that will be when I will be operating. But that's the first time for me. We have the legacy. This is the legacy course. It was taught by several faculty. Kinzel was teaching that. The Rinsons were teaching. But of course, the guru who just finished, retired. He just retired. He became just now, announced last week as a professor emeritus, a very famous guy who used to be distinguished professor. And he was number 5 aerospace engineering specialist in the world because everything is red. So there's a ranking of all aerospace engineers in the world. Like, I don't know, millions of them. But he was number 5 in the whole world. And he was sitting next to me next to us. And it's the Gordon Leishman. So Leishman wrote this Bible of helicopters called helicopters dynamics or something. And that's what everyone uses in helicopters industry, academia to learn about rotorcraft. So he just retired. I got this information about this yesterday together with this short notice from our department chair. Okay, that was part of the department faculty meeting, which I of course missed. To show the slides. Anyway, but you see a lot of the different things. Our acoustics is a big thing for us, but that's not really quite often. Otherwise, computational fluid dynamics, advanced computational dynamics, advanced compressible, etc. All those things usually people take and then after they finish undergrad. So in the 5-year courses actually can be taken by undergrads as well. Even though it's a graded program, but the 500 level can be taken by undergrads. 600 no, it's basically like PGG 30. And it basically extension on this thing. Anyway, so we have more courses now. And of course, there's also courses they can take from mechanical or like other departments if it's because you have listed as like those which are eligible for credit. Here's the point. Yeah. Well, a few girls there because we don't have many. Yeah, we don't have many. Yeah, that's the same as everybody. You know, not really. Yeah. anyway, doing some design. That's very good. So we have this history. As I mentioned, 1926, that's when we established. So Kigby Embry and John Embry-Riddle, the two pilots, and they established this first school of aviation, Embry-Riddle School of Aviation in Miami. And 50s, so you see, like for so many years, it was strictly pilot school. In the 50s, they started aeronautical engineering technology. That was just technology. 60 established PS and aeronautical. So around 60, they moved to the top from Miami. Then in 86, finally, it was established very recently now. It's American Aeronautical Engineering, Space Engineering changed, moved to Lehman Building, that's 95. So that's how building is all over. Like that. It's almost 30 years. Yeah, we're up to the new building. In fact, we don't have enough space because the number of faculty over the time, like 20 years that I was there, like, more than doubled. Like the number of faculty more than doubled. The number of students, I think, tripled. I'll show this number. It's good. And then, yes, we have concentrations. So in 2000, that's a big, like a really big event for us. So we started the PhD program only in fall 2013. And as I mentioned, the very first student, PhD student was my student lab. Nguyen, I'll show the picture of him. He's now like a chief leader already, in group leader in I think integration and Lockheed Martin. So he's a big guy now. So that's a I see it. It's in 21, but the idea is the same. And I'll show you the numbers, which is like this year. So small class sizes, that's a big thing because usually people like I go to other universities, they have like 200 people sitting in our dorm. We have like 30, 40. But then we have many sections now because we have so many students. So we could have like 4 sections of jet propulsion class, for instance, the same time. So people like speak to those. We have honors program. Yeah, that's Sigma Gamma Tau. That's the honor society in aerospace. I'm a member of it. Also Sigma Gamma Tau. Okay, so we have fraternity. This is actually what they call the honor society. We don't have fraternities and sororities. If you're really up to party life, that's not the school for that. For the party life, you go to Florida State or UF. Florida State is best. If you go there, that's non-stop. That's probably a way to go doing the movies like American Pie or something like that. That's all about life there. It's a lot of like interesting things going on happening. So great part of that for studying. But we only have like honor society. It's only like geek Greek society, geek Greek, and things like that. Yeah, that's very university is very prominent in design. So we have a lot of design courses, preliminary design, advanced design, detailed design, etc., etc. So all these courses are both in aero, areas, both jet propulsion for aircraft, propulsion. They all have these things. Really big design. That's what we're very famous for. But one of the best designers came to us, and we produce this design courses. But we always a big thing. And of course, the bed. Do you have the EBIT like here or something? Similar.
Our universities in growth. Yes, they're not. I think.
Yeah, because it's a pain in the neck for everyone using it. You have to do accreditation. So, and that's one of the problems when you try to do any kind of dual degree with any other university. The first thing that comes and cuts the whole thing. Are they accredited? How can we do like accreditation with them, etc., etc.? Because it's a very strict process. So we cannot just take like courses from outside the country or from outside the university, which is not accredited, not take. So that's a big thing. Otherwise, the degree will not be accredited. See, this is like a loop. So high-tech facilities, Microplex, that's like there's a research park, which is established for like technology development of some companies and hybrid aerospace things, etc. So we have this new, well, it's not that new now anymore. It's like 8 years or so. But that means everything was new and new Eagle Flight Research Center. Now we were very famous in the flight testing. So you actually have the because we also at the airport, right? So we have the whole fuel planning, so the whole fuel planes that basically do the testing right in flight with some particular components, like maybe some propulsion components, some other things. So, and this is actually a very interesting thing. So this is part of this hangar we have there. I'm not sure what it is, but it's actually very new right now. This is actually a new facility for the new wind tunnel. This is actually that very guy, Gordon Leishman, was like the guru of the helicopters. So it's probably like when he was just establishing things like 6 years ago. But he was like very, he's a Scottish from Scotland. Of course, everything should be perfect. If it's not perfect, bye bye. So he was always angry about things, particularly with this new rules about this post-tenure review. He basically said, "Heck with you guys." Although he could probably have no problem at all. But for him, like to have some kind of review, he's that distinguished. He's the best, and he was just very angry. So he said, "I don't want to do this." So it was very angry. Yeah, we have a lot of things with internship, by the way. There was some questions you asked about. Yeah, we have some internships. It's very usually a lot of particularly engineering students. They get internships in the companies like Boeing, Lockheed, etc., NASA over the summer. So they go and work somewhere else. And then they come back to the fall semester. And usually have no problems. In fact, since we have twice a year like job fairs, where like 100 companies come from our space and have a big we have this big facility and but it's basically like a former athletic center. And so all these companies come and they take the whole space for the booths, and people go there and take the interviews. So there's whole lines of people, like for instance, who interview with Lockheed or some other company. And so they get internships, and then after this internship, of course, they have no problem to get a job. Because once you go once, you become like a family member there. And that's why they get involved with the, with these companies early on, before they even before they finish the so we get the position. Anyway, 6 months of the graduation, as you can see here, this chunk of them go into military or employed. Well, military is one with their other continuing education subject. So mostly you see it's all employed, goes to the industry. Some continuing education to masters, but very few. Other, I'm not sure. It's maybe just like my student. He got a master's in aerospace engineering. He got a thesis with me. We went to Air Force, like Red Patterson Air Force Base for the summer fellowship several times. But he was an interesting guy. He was like a hockey defense player. In fact, he was a coach of the defense team at the Embry-Riddle hockey team Holland Shade. And eventually, after he finished all this, finished the defense, everything, he went back to work with his dad as a mechanic, auto mechanic. What was the reason in general? Actually, I have another example that's recently. Garrison, another student, he was from Montana, state of Montana. His family had farms, cowboys, with the farms, with the horses, etc. So after getting his aerospace engineering degree, he went back to become a cowboy again. So, I don't know. This happens. These things happen, but I don't know the reason for it. But anyways, you'll be like really, really educated God. So that's probably obvious. And yeah, we do have a lot of military. As I said, there's a lot of it's a big military contingent on campus, and they will continue probably that. Ranking. So you're all familiar with the US News and World Report ranking system. So that's like what everyone watches, like all the families look, what is the best school, what is most expensive, because it's like US News and World Report publishes this ranking. It's like a big brochure with all possible things, like the best out of space, the best this, but anyways, for 16 years in a row, we were #1 school, but when we didn't have the doctoral degree. Because the doctoral degree schools have a different ranking. So they're like different area. So that was the issue. Now we rank #5. I'll show you. Now we tied with Michigan because we now started doctoral degree to follow. So that's an issue. Graduate school is still like #32 right now. But we're catching up. So lots of competition because again, we have like over 100, I think, tuning clubs. You do this competition like coming next or something. So we have these competitions, which is usually organized by AAA. So this is our main society, American Institute of Aeronautics and Astronautics. Usually, I encourage all students to become a member. That's our main professional society. So we're all like part of it. So all conferences we go to is AAA conferences. Well, this is me go there and grab someone to see. And so there's all kinds of competitions, particularly important as DBF, design, build, and flight. So that's actually you build from scratch some plane and you fly some rules, do something. And for many years we were number 2, and now we're number 1 in 2024. We got number 1. Actually, the advisor was Lishman. So can't understand why he's so angry. I mean, you get all kinds of like things you should be proud of. Anyway, but all kinds of things. First place, there's you see all kinds of things. Even in 2015 was the last revolutionary astronautics concepts, number 1, 2. And 7 of our graduates are astronauts. So they flew in space. 7 of them. First code is like member of the board of trustees. She is like main sort of ambassador everywhere. So this is like the most recent like RU Purdue is number 4. But before us MIT, Georgia Tech, Caltech, then Michigan with us, Stanford, Texas, something. This is the Skype's team, which got this first prize. This is students. This is what they built in blue. I'm not sure what the details completions are, but you got the first prize, so they're pretty happy. So this is up to 2021. You see how things were going up. It's basically our undergraduate enrollment in the fall of 2020. I think 2. It was going up from 12 in 2012. Look at that, from 1,200 to like 2,000. And then if you go back to like graduates, so there was like little to 2013. That's when we started PhD, right? So we're going. Now it's 57 in 2022. Now we have 70. I'll show you. And then everything is going up. This is the lead. And then, by the way, the research expenditure, how much we spent in terms of money on everything. You see, it's growing. Like PhD research before it used to be mostly teaching. Now it's primarily research. So it's becoming more and more research school. Okay, so I'm very good. So this is the enrollment, the latest data in fall 2025, almost 2,400. So we doubled in 12 years the number of students. You see, this aerospace engineering alone, it's not like university. It's our undergraduate degree in aerospace engineering, 2,400 students. Unbelievable. I think number 2 is like Georgia Tech, like half of it. And then the rest. So we're like way. And then PhDs, we have 71. Masters 108. I like PhD more. Because usually PhD is basically what people can commit. They commit for 4 or 5 years, they do research, they can do something. Masters, they want to like finish in 1 year, that's it. So if they finish in 1 year, you basically just give them something and they bye-bye. That's it. I mean, there's no like time for any kind of meaningful research. So that's usually the bad thing about masters. So we don't even usually offer for internationals, specifically, well, for everyone. We don't really offer much support if it's master students, or only very select. For PhD, everyone is covered, of course, because they all come from countries which have no. Right. So this is actually the tracking of the COE tracks by semester. As I mentioned, the first 2 years is pretty much like combined. Like this is a fundamental engineering program. The first year, everyone takes the same thing. All different departments do the same. Then in the second year, there's a split between like computer guys, electrical, and the civil, mechanical, aerospace. There's different courses. That time, in the end of the 4th year, fourth semester, second year, they make the decision who's going to be going to aerospace and who's going to somewhere else. Okay. So this is going to be the split, 5th semester, 3rd year. Okay, so And then eventually in this last year of the undergraduate program, that's where there's a clear split between aeronautic, jet propulsion, astronautics, and rockets. Usually people do this or that selection, so they can take courses in any of those. And of course, a lot of people do into astronautics. Thank you, Elon Musk, because everyone is trying to do like some space stuff. But still, we have a lot of people still doing aeronautics, and especially now, as you'll see from my presentation, aeronautics becomes really big. We have a lot of different things going on in aircraft. And so it's a really interesting time to be there. So basically, this is all split with what happens for different people. Like if you do, what are those who actually want to do aeronautics? So this is the people interested in broad knowledge about atmospheric aircraft. So that's about aircraft, right? Airplanes, helicopters, unmanned aerial systems, events, so all kinds of things. Areas, aircraft design development, again, that's the biggest thing, which is undergraduates can get. So finish. Design for specific requirements, aircraft design, design of conventional aircraft, applications, performance, stability, control, manufacturing. So these are the companies that hire our students. A lot of them go into like Airbus, Boeing, Bombardier, Beechcraft, Cessna, Citrus, Gulfstream, Lockheed, name. Cosmetic. So we go there. Going. So this is not really new. Everything was new like 5 years ago, 10 years ago. Things go like very fast. So urban air mobility, which is the area which I'm talking about the most. This is what we're doing right now with NASA. This is of course like flying cars concept. That's what we're going to talk about. This of course is now becomes the mainstream. Flying wing designs, some systems, vertical takeoff. Well, eVTOLs, particularly, again, that's the same. It's electrical vertical takeoff and landing aircraft. That's what you definitely need to develop in Colombia. That's your future, guys, because that's how you're going to fly it. Between like here and Manizales and Medellin, not go to Bogota and there, just go straight. It's like a taxi. Or they go over the reach, you get right over. So that's definitely what we need to talk about. That's something we should do. Companies like Joby or Archer, that's the company we have to really development very interesting. Would be very interested in this because the first thing they talked about was flying in Dubai. Of course, Dubai have all kinds of money they need to invest. We're ready for everything. Not so much now, but I mean in general. Jet propulsion, yeah, a lot of things related to jet. That's of course I teach to jet propulsion, right? Although I teach aerodynamics as well, I teach CFD, lots of different things. So air breathing engines and jet propulsion, all kinds of things. So you can design the turbofan, or turboprop, turbojets, or ramjet, or scramjet, any of those things. That's actually what you can get in this area. Those things, of course, there's companies who hire all the main engineering, like the propulsion companies, Pratt Whitney, GE, Rolls-Royce, Honeywell, all those things. Main companies that hire in this areas. So there's a lot of things here. Of course, cycle analysis is the biggest, right? So you do cycle analysis part of the jet propulsion course. That's how you design your, like preliminary design of your engines. We move to the most sophisticated stuff. And of course, most sophisticated actually involves CFD functions, right? So you need to do like computational analysis to understand the motoring process and everything else. Materials, the combustion, a lot of things combined. Extracurricular activity, yeah. As I mentioned, there's zillions of student clubs. It's like literally we have this student club fairs. It's the whole campus is actually filled with a booths of students showing how they what they do. Not just like particularly for the design and stuff like that. You also can do like scuba diving or like some other things. So there's a lot of interest club. Or sailing club, of course. We're just next to the ocean, by the way. We're just next to the ocean, so we have a student presence in the Halifax Halifax Sailing Association, HSA. So there's a big thing where you have dealings of different sailboats, and you can just go there and sail. I mean, that's a big thing. If you like sailing, I like sailing. So that's a big thing. It's also, by the way, aerodynamics. So aerodynamics can be applied both to airplanes and sailplanes, sailboats. So it's yeah. So that's like also bicycle, right? You have to be designed for the competitive things. I had some faculty, some students who went to be designers for the new generation of bicycles for these big competitions, for instance. Because they do very aerodynamic shapes and all. So aerodynamics is everywhere, by the way. If you think about it. Like what researchers involved, yeah, all these things. Astronautics, that's actually something which relates to the extraterrestrial activities. So you can go to Mars or somewhere else to design this kind of like satellites or some sort of I don't know, rovers. So people are involved. We have faculty who are involved in this very heavily to design some sort of Mars rover, for instance, or some cube satellite. I'm not sure how much I'm doing this thing, but in the school, they lot of things with space again, and takes Elon Musk to die. A lot of things. Performance. You have the sounding rocket, cloud called Icarus, that Dr. Perel was doing this for many years. I think it's like somebody else is doing all this stuff. And rocket propulsion, well, I think you rockets, right? It's rocket propulsion, propellers, yeah, that's what I'm thinking about. Many clubs as well. Now, let's get to the actual area of research for all groups, but there's several faculty involved. I'm just director of the lab. We have a number of faculty and a whole bunch of students. We're involved in activities in the lab. This is actually a lab. The first PhD student I was talking about from Vietnam originally. He just had a baby with his wife. So she's very happy. Probably, I'm not sure. This is actually my collaborator for many, many years, and he's a founding dean of the College of Engineering. That's Dr. McBuddy. That's him. This guy is somewhere at NASA. This guy in Hawaii. But our faculty member from Romania, I think very interesting guy, doing all kinds of controls. At some point he said, I just want to live in Hawaii, sorry, bye-bye. He went and he's actually established his own company in Hawaii. I'm not sure what he's doing, but must be very happy. I think he's surfing most of the time. I'm sure. There's another guy from India. This used to be DOD guy, but then he left. He's from Eglin Air Force Base. It was a scientist there. We collaborated with our reports. Anyway, people change completely. And we just have two of us left. Look at my buddy and myself from this group. Everyone was wow. But I'll show you later in other presentations the whole group as it stands right now because it's interesting. We have like I don't know how many countries with students. So this is what you'll see the poster next to the door to the lab, which actually like again shows the thing, but then very briefly shows the whole different colors from different projects we do. And so I will be elaborating as part of this presentation on these different projects, one way or another. Some transitional airflow, instability stuff, some gas probe and turbulence, and jets, etc., etc. So you'll see a lot of things, which will show later. So the main thing. So I was like in 2010, I was researcher of the year at Embry-Riddle, like best researchers. So I was actually, that's funny. They decided to start this at that time to decide the tradition that the researcher of the year presents his research to the whole university at the huge main auditorium. Is like celebrity home. And so I was the very first one to do that. And honestly, I was the very last one. I was the only one who started, and they decided not to proceed because I guess the administration was frustrated. I think they couldn't understand the word, so they said, "That's it." But finish the thing. So I was the first and the last. And this was actually the title slide for that presentation because that's pretty much what we're doing. It's a multi-fidelity numerical experiments in aerodynamics, acoustics, aeroacoustics, and full should add propulsion as well because we actually have. So it's all numerical experiments. I had to like calculate, but it's actually multi-fidelity. we're actually moving very rapidly into the area of multi-fidelity or variable fidelity code, where you actually combine various tools which can different fidelity levels, and they need to be very let's put it away, verified and validated, and that's one of the biggest things for Gilbert. So in this presentation, let's see how much time. Okay. So this presentation is very introductory. So what I'm planning to do is to show basically the slides, like one slide per project, what we were doing recently, because other projects specifically will be like focused on the next presentations. And so I'll be kind of like circling or spiraling. There'll be more emphasis in some areas, and then even more emphasis later on. So they will like sometimes I will address 3 times the same project. So you'll see that will be more and more detailed. So at some point, once you repeat 3 times, maybe you'll understand that. Repetition is the mother of learning, right? So you have to do that thing. So very quickly, what we're doing, like a lot of things we were doing with flow control. So flow control is a big thing now. So you can control aerodynamic flows, but also for acoustics, for propulsion. There's a lot of actuators which do this. There's a lot of closed loop control systems which do this on linear ones. This example is actually where we started to do a lot of things related to synthetic jet actuators. I'll talk about this specifically later on. There will be separate presentations. And this is really the tool for us to control the flow by controlling the bound relay. That's one of the things which we're big in. And that's how I actually got my grants, for instance, in the beginning. So for instance, we're trying to control the aircraft with synthetic jets instead of aerial. So there will be no mechanical like motion anywhere, like devices. You just basically have microjets, arrays of microjets, which can pretty much control your flow and this control your angle of attack and that control your moments and everything. That's the idea. So we tried to do this, then we did the steps on this research. I'll be talking about this again. To the noise control, to the even icing control, you'll see that later on, and all kinds of things like that. So, but this was the kind of one of the things first. This is an example of how we basically inject flow as a microjet into the bound relay and basically can change the dynamics of the bound relay by this you change the overall dynamic features of the entire. This is actually how it puts up. Yes, the jet actuator, for instance, is a small cavity which is embedded inside the full surface, and this cavity, like a concourse resonator, and it's actually this small orifice, and basically you have this diaphragm which starts bouncing back and forth. It's piezoelectric, so you put some voltage, you bounce back and forth, you create this difference in the pressure, so it creates a jet, but it basically goes in and out, and that's produces this effect on the boundary. So that's in a very brief thing, because again, I'll repeat it again and again. So a lot of things we were doing, of course, it's very important. What tool do you use? So for many years, I was the fellow at the Air Force Research Lab, Wright-Patterson Air Force Base. I would go there every year for 15 years. That's how I'll take my students, lab, team, others, basically we're doing research with the flagship code of Air Force. So we know we got high fidelity codes, right? That's basically Navier-Stokes solvers. They're very powerful. Pretty much they can do almost DNS, so it's like direct numerical simulation. You can do that, but it's very expensive. So most of the time we did what's called ILAS. It's implicit large eddy simulation. So I'm not sure how many are familiar with this term, but basically that's the best you can do in a reasonable amount of time, 3 months sometimes, to calculate the actual flow around whatever, anything in the world. So that's basically a solution to the press about staying on the place. So conservative form, it's very high accuracy, 6 order comfort difference in second order implicit time matching. Now, I'm not sure how much you know about CFD, by the way. Do you know anything about CFD? You haven't heard about this. Have you heard the word? Okay, this is computational fluid dynamics to talk about. So that's what it is. And so if you come to like study with us, CFD will be the primary thing you're going to be doing. So that's what people do now. All the industries, everything. That's how the SpaceX fly. Everything's about CFD. So that's how you model and predict and design. So that's things I could do. Anyway, so all kinds of interaction of gas, water, turbulence with the aircraft structures, the effects of this, like when you're flying in the aircraft, and you start bouncing, you're like crazy about this thing. It's called turbulence, right? You say turbulence, please. What is it? Put your seatbelts, sit down. Right? That's what they tell you in the aircraft. So this is the turbulence interaction. So we're studying this turbulence interaction with the wings to understand if they fall. If this, we know that nothing will fall. Shouldn't be afraid of that. But in terms of reaction, yes, it's important how the aircraft will react. And maybe some are elastic things, elasticity, right? For instance, you can get on the flutter. It used to be that the wings did fall off in the 30s. People had no idea what's going on. The aircraft were flying, all of a sudden, boom, your wing is over, and you're done. So the thing is that people could not understand the phenomenon until in the 40s, Dorson came in the US and explained the entire thing. So he analytically explained, and he showed that actually the envelope where you have to be to avoid this kind of condition. So what kind of structure should be, what kind of flow should be, etc. And that's how everything is designed these days, not to get in the unstable envelope. So then that's how we don't get into fluttering. That's why we don't lose the wings when we fly. Right? So it used to be like nobody knew, but now some guy comes and he opens that. So, and we do a lot of research on elasticity, by the way, but we do it the opposite. Flutter for us is a good thing. I'll show you how you actually can extract energy from flutter. That's a good thing instead of the bad. But it used to be always the bad. Anyway, this is our Vega cluster. This HPC system, high performance computing. So we have like zillions of, I don't know how many nodes. So we do parallel computations in parallel for CMD. That's the big thing. This is actually the utilization of the airfoil. Is all the vertical structures, etc. That's how they behave on the airfoil. Like there's a gas interaction. They have the bond layer collapse, basically being wiped out by the turbulence and gas interacting with the bond layer. So just finding fluids research in general, we have many things. Like right now, the biggest is NASA, like $4 million we do for just for us. Altogether, no. Yeah, for $4 million is actually for our team. I think Embry-Riddle has 1.4 million. That's the one I'm in charge of because I'm PI, principal investigator. That's how I get all my students, like 5 students covered, like you start at institution, all these things, and I have 2 more faculty, like my body, for instance. So that's how I spread all these things. Anyway, with the many agencies, Air Force, NSF, National Science Foundation, United Launch Alliance, used to give us tiny bit of money. If you think about that, that's the guys who developed the rockets with NASA. So, and they actually were failing miserably, but now they actually were. They're the ones, I think, which finally launched this thing, Artemis, together with NASA just like a few days ago. But everything was delayed. They like really, because it was a venture between Boeing and somebody else eventually, and NASA was basically supervising the whole thing. So, not as efficient as SpaceX, but for instance, the Blue Origin just flew fine. It took them a while too. So it's a tricky business to do the rockets and fly and get to Mars finally. So that's the idea. So FCAP for many years was supporting us with a tiny bit, but FCAP is actually an interesting thing. That's what we dream to develop. FCAP stands for Florida Center for Advanced Aero Propulsion. So this was a consortium of 4 universities with Embry-Riddle as part of that, but the main was Florida State. And they were getting the biggest chunk, and then they were getting, it's a state money. So the state of Florida gave money to establish a center, and they were the ones who distributed Florida State. And we were getting some money, but not much. But now they have the whole building built, huge building, just for Florida Cap, this FCAP. And they're enjoying this very much right now because the money is gone, but the building is there, and they still get everything they want. And actually, industry does support them now because they get this connections now as part of this first 5 years. It was like establishing connections. Now the industry goes to them for any kind of requests. That's how it works. So right now we work mostly on NASA and ONR, Office of Naval Research. That's DoD, that's name, and that's where we do the, for instance, research on the. That's what Juan Felipe is doing. That's actually his whole thing. He's working on this water bubbles as means to control the noise from jets during the takeoff. take off from the aircraft carriers. So all the jet running on aircraft carriers, when they take off, everyone becomes deaf. It's very extremely loud. So there was the idea to design some sort of like a way to control this noise. And so we proposed several means. In fact, that we used this for the ULA research because we were proposing, or NASA Kennedy Space Center was actually supporting us together with ULA to design the idea how to suppress the noise, because I don't talk about project, I forgot about this. Suppress the noise at the takeoff. So at the takeoff, there's a huge jet coming and bouncing from the surface of this launch pad, right? And then this becomes acoustic, nonlinear acoustic waves which propagate up, hit the surface, the structure, and propagate all the way. It can destroy the whole payload. So that's a big thing. So they were asking us how we can like control this thing. So there was ideas which actually is right now we model them, but they implement it. It's basically water infusion. So there's a bunch of water which is infused at the start in these jets, and that suppresses a lot of acoustic load. And that's a big thing. So the same process actually we're proposing for the Navy. Through some modification, but that's the thing. So Fulbright project. So in 2003, I went finally to. It was everything was delayed. I got the award in I think 2000, and then it was COVID. So Fulbright completely closed. Department of State, like everything's closed, and so it was basically started finally in 2002, 2003. Anyways, so this was a 2-year project at Kazakhstan. It's Nazarbayev University. It's cool, very big, and it's very rich school because it was all the stolen money by Nazarbayev. Whatever he stole, he was not just he was a good guy. He stole, but then he invested in some of this and some good things. So he invested in Nazarbayev University and his name get it funded. So this Nazarbayev University was established in Astana, which is capital of Kazakhstan. And so they spend a ridiculous amount of money to bring all the best faculty from around the world, from Imperial College in London, from Delft University in Poland, the best universities. As you know, ridiculous money spent on all the equipment for the experimentalists. The guy, like a very famous scientist, I met him because I was going like rounds and rounds of introductions with everyone. So he's a very famous guy from Delft, and he was telling me, "Oh my gosh, I got it! Like there was so much money, I got equipment I never dreamed about in Europe, but now it's all here." So he was just showing me. Anyways, Nazarbayev is gone. You know, imagine he's not still in prison. But the thing is that in the end, this thing is there, but the money which is now really released to this university is much less. So the people go away because they don't have much salary anymore. So it's interesting what's going to happen. But that was the point when it actually was already dwindling down, but still there. So at least find one guy who can do some collaboration with it. Right? So that was the thing. So as part of this Fulbright project, which I was announcing, was basically ecology is a big thing. Ecological transport energy, something green, really green. So we talk about the green, of course, yeah, the air taxis will be green. It's eVTOL, electrical vertical takeoff. Everything will be green. The green energy, so we talk about the project with NASA, with NSF, sorry. NSF was supporting us with Israel through the joint NSF-BSF project. BSF is the Israeli Academy of Science Foundation. So anyway, so we had this, they did the experiment, we did all the numerics and all that. That was the getting energy from flutter. As I mentioned, flutter is a bad thing usually. Flutter is the interaction between the wind and the structure. You probably saw it, like in the wind, sometimes you look at the fence and start vibrating, it's flutter. So if you do this thing and you design the structural property properly, then you can actually extract very efficiently the energy from this motion. So this just wind interacting with the plate, creating the scene, you can get this from the plunging motion out. So that's the, so we did this, but people try it. Of course, it's been around for many years, forever. You could see it like probably dinosaurs so as well. So, but it was never controlled because if it's not controlled, it's very chaotic. It can be going up and down. You just never can control. What you can do, and that's what we proposed, and that's where there's a patent. Now we have a patent on this thing, so you can put a very special shape I'll talk about this, but it'll be separate presentation. For this kind of airfoil, we call it MG airfoil, modified glowered airfoil. And basically this airfoil in normal condition have separate flow. You see from this airfoil. But when you put the synthetic jet actuators there, and you put them and you basically actuate in sync with your natural plunging frequency, all of a sudden you have a very controlled and very powerful plunging motion. And that's the thing which we actually proposed, and that's how we got money from NSF, but we still get money for STTR. And that's something I'm going to investigate further with it. Maybe we'll do it for the DOE part further. This thing. Anyway, the idea is that this particular airfoil produces a magic. Any other airfoil, if you do NACA 0012, will not do this because you cannot control the aerodynamic moments with synthetic jets. It's just tiny bit. But if you have this thing controlling the entire separation by like rotation, the flow all of a sudden on each side, in sync with the natural motion, then this will be very effective. And that was the idea. All right, so we'll talk about this project later on. Of course, lots of noise sources. We're dealing with this air taxis. So that's one of the big thing. And this thing is another project. So icing control, I mentioned before, that's an interesting stuff. We actually use synthetic jets, heated synthetic jets. If you heat synthetic jet actuator, like the air inside, you have some sort of, all of a sudden all ice is gone. You probably don't care about this and you don't have much else. But people in Canada, Russia, any kind of country that just produces kind of a particular condition, it's really dangerous. And people people right now have, if you've ever flew into the north, usually your airplane is delayed like by 10-15 minutes because you need to get to this thing which is like sprinklers, and they sprinkle special type of liquids like de-icing liquid on your aircraft before it takes off. That's what's naturally they do to prevent. But sometimes it doesn't work. You still have a lot of accidents happening from time to time. And so this thing actually works like magic. We show this, and I'll show this in another presentation. All icing is gone in a sec. Actually, it's not. It just prevented. It's now out. In this case, that was an interesting thing. That's a very busy slide. There was a poster for the Festival of Science in Washington some years ago. So at that point, we were actually thinking, can we use those synthetic jet control aircraft as drones for exploring Mars or any other planet? So this is like you see puff, we call them puffer drones because they puff the air, the synthetic jet puff the air. Puffing the puff drones for the extraterrestrial exploration. That was the topic of this thing, and a lot of things we're discussing here. You basically need to run simulations with the conditions on Mars. Atmospheric conditions is different a little bit, but it's still you just have to do the dynamic similarity rules, Reynolds number, Mach number, all these things. If you do it properly, it flies like magic. Everything's fine. So we did this thing, we explored this and showed how we can do this. So it was very nice, interesting stuff. All right, that's probably would be very interesting to Dr. Guillermo. So he's doing the controls and the instabilities and everything else. So this was a project where the Air Force came to us and asked to help. Because the idea was, there was, I don't know if since you're in the stability, there's a guy called Amitai. He is in Rensselaer, the RPI, right? Rensselaer. So he was doing the experiment how you can control instability in the boundary layers on the airfoils, on the wings in general, right? And the idea was that he was actually put some experimentally. He was putting some actuator, some like actually mechanical actuator. It's actually moving up and down, like tiny bit. You can barely see that going up and down. It creates the excess instability wave because in the boundary layer is a shear layer. Every shear layer produces basically have the condition for the stability to develop. It's called Tolman-Schlichting waves. So this Tolman-Schlichting wave, you excite it with specific frequency and amplitude by some sort of mechanical actuator upstream, and that's what he did experimentally. So he did this, and then downstream he put another actuator, which is supposed to suppress this instability wave. So he was trying to design the idea how you can do the actuation in a way that you will suppress the upstream and delay transition. That's the whole point. How you delay the transition from a laminar to turbulent. Right? That's the big thing. And so he did this, and you can see there's like what happens on the surface. So if you do this, of course, if you do the open loop control, it's quite clearly you need to have one wave, the same frequency, but anti-phase. So you kill the phase of the first guy. That's how you kill your instability. So in the open loop control in the experimental setup, it works, pretty reasonably. So you have this instability which grows into turbulence, boom, almost have nothing. So it works. So we try to do, and then Air Force tried to do this. It's all flat plate. So on the flat plate, they did this, okay, we do it numerically. So they did numerically the closed loop control system to see how you can actually do this for any kind of frequency, any kind of amplitude. And it works. So you see this instability grows and it decays. They could do this with some level of success. They had nonlinear closed loop control system, but very basic, very basic. We actually were prominent in doing very sophisticated nonlinear controls with this guy from physics, engineering physics. So we tried to do the same. And then they went to the airfoil shape, real airfoil shape, with the like camber and everything, like thickness. Nothing works. Nothing works anymore. No matter what they try, no, nothing is suppressed. You like tiny bit, then it goes back. And so they asked us, can you do it for us? Can you see if you can do any kind of like nonlinear controls? So we tried, and it didn't work. So that's one of the unsolved problems in physics, guys. If you ever want to solve it, please be my guest, because that's a very tough problem to deal with. And in fact, the idea is that you can actually control any kind of instability, and eventually, because you don't know what's going to happen, right? It's going to be any kind of disturbance, which has been exciting. And we have the idea that with the actuation, with the proper actuation, which is controlled non-linearly with the feedback loop control, you can basically suppress it, the whole bunch of these instability waves, and basically delay transition and decrease the drag and increase aerodynamic efficiency, all these big pluses, all the big benefits, save billions of dollars, right? So this is a big thing. And but so far there was no, we actually used the technique called POD, proper optimal decomposition based nonlinear control. It was very sophisticated, very powerful tool. It's a lot of positions there, but still didn't work. We don't know what's going to happen. In fact, it was such a frustration for the girl who was doing this. She was doing the master's. She was continuing to PhD, and then she was like failing. She was like crying and said, "No, never again. I'm going to touch this damn computer." So she wanted to become an experimentalist. Nothing worked. So that was interesting. Well, yeah. So this is actually how it looks like. You see, this is the real shape of the airfoil, and no matter what you do, it's still like you can slightly suppress it and boom, it still keep going. You'll keep increasing, so you still transition. Maybe you can delay by a tiny bit, but it's not really what we hoped for. But maybe it's impossible. Maybe just physically impossible, because you always have this, especially with the separated, with this kind of thing, you basically have a very, the boundary layers get thicker, right? It's an inverse separation, so you basically have a lot of things going on, a lot of mixing. It's difficult to control. Since boundary layer becomes big too. So TS waves are slowly growing. I'll show you later the example. Then when they move to KH wave, KH, Kelvin compounds, it's invisible instability. TS is the viscous instability, that's boundary layer stuff. They can actually move into KH wave, transform into KH wave when you have the laminar separation bubble. Because laminar separation bubble basically sustains the inviscid instabilities. It's separated, so it becomes inviscid. And that's where it grows exponentially really quick. And this actually will be the part of the talk which I'll be going transitional airfoils, because that's basically magic. What's happening there, nobody could explain why this thing, like all of a sudden the airfoil becomes like a jet nut problem. It's just because of this thing. Huge feedback, because all of a sudden you have transition from TS to KH. And we were actually the first one to explain the whole thing and publish a bunch of papers. It was very interesting. But I'll talk about this. This is just TS. It's slowly growing, but it transitions. And when it transitions, you lose your, efficiency. So that was a good question. All right, I'll be having a separate presentation on the active jet noise control. Again, that's a big thing for the Navy, even more than, everyone, Air Force as well. But we were trying to figure out how to control the noise from the jets. That's one of the oldest problems in aeroacoustics. In fact, it was the first problem in aeroacoustics. Ever since Sir James Lighthill, invented the aeroacoustics as a field in the 50s, that was the primary goal, to suppress the jet noise because the jetliner started to appear at that time. It was extremely noisy. Nobody knew what to do with them. Then there were a lot of a generation of people who came, like including Chris Tam and others who were trying to like explain what the screech tone is coming, what is there, and other things. So we just continuing along this line historically. And of course, Dr. McBody was the chief scientist primarily on jet noise as well in the NASA Glenn Research Center, or he joined Embry-Riddle. So anyway, so I'll talk about this in a separate presentation. We also do nonlinear controls there, also use synthetic jets, see. But you also can do other things. For instance, you can do the plasma actuators, other things. Of course, those are all active control. The passive control people use it. You probably see that, like chevrons on the jet nozzle. So that's very classical thing now to suppress speed of the nozzle. To full extent. All right, this is a project which is really fun. I'll talk about this. There will be separate presentation on this project. This is actually a fan wing design. So this is a wing with embedded centrifugal fan. So this is actually another active control device, right? So the centrifugal fan acts right there to produce extremely high circulation. Circulation, you know what Joukowsky theorem is? You know what the lift is? Rho v gamma. It's all proportional to circulation, the power circulation. So the higher the circulation, the higher the lift. So this is what's called e-stall device. Extremely short tape or landing aircraft. So it can be like not vertical, but very quick. So you don't need much of the takeoff area. So we actually did this kind of analysis, but for me it was fun because it was really interesting historically how the whole project appeared. That's one of those things, legacy of the Soviet Union. Well, anyways, there will be separate presentation. I'll talk about the history there. Dynamic soaring. So there will be again separate presentation on this research notebook. I'm not going to talk much about this, but this is what called albatross flights. So we're trying to design this aircraft UAV, which will be flying pretty much without much battery. So it will require some, but not much. And so basically, ever since Rayleigh in 1886 published his paper talking about there should be a way to do these things if you have non-uniform flow, and that's true. You have to have a shear boundary layer, atmospheric boundary layer, for this thing to work. So what these guys do, you have the flow with the boundary layer, as you can see here, the shear flow, and this shear flow is actually employed by the birds to extract energy. So they can fly indefinitely long without any kind of thing, and basically even they have the special locking mechanism in the wings. They can sleep. They fly a big, they sleep, and that's it. They don't even need to land. Well, they need to land sometimes because they need to have babies. But for the most part, they just fly, and they can circle the whole Arctic, without doing anything. It's because they have energy coming from this thing. Well, they still eat, and we'll have still better. So that will be complete simulation of this thing. And that's how they fly. Well, actually, that will be again elaborated later on. But the idea was for us for the project originally was not just to look at how this thing works and to do the other pilot, but also see if we can do various types of geometry changes, like variable span, variable sweep, variable dihedral for this type of aircraft. So it will be actually more efficient during the flight. So that was another. But where's all things? Yeah, that's just some tools I'll talk about. All right, so this is a big project on the feedback loops for transitional airflows. I was mentioned before, that's when TS moves into cage, right? And that's all relates to the various types of mechanisms of noise production in general. What happens on the airfoil? There's a lot of different things which may happen: laminar boundary layer, vortex shading noise, turbulent boundary layer, trailing edge noise, separation stall noise, trailing edge bluntness noise, vortex noise. All those things are possible mechanisms for noise production by the airfoils, and specifically, by the way, for the blades, not just for the wings, but for the blades of the rotor. So right now we're doing this research with NASA on the rotorcraft, and that becomes a big issue also because the regimes of the operations for these blades, not traditional like helicopters with the very high Mach numbers. These are actually low Mach numbers when these mechanisms, which is called the broadband noise mechanism, or sometimes tonal noise with the acoustic feedbacks, they become most prominent. Never before they were for helicopters, but for these kind of devices, that becomes a big issue. And that's what we're exploring right now. So I'll talk about this in big detail later on. Yeah, in this particular project, it's all about this feedbacks which produces, if you look at the spectrum, you know FFT, right? So FFT basically produces a spectrum of noise. You know, this is called broadband, when it goes to like some sort of like no tonal still. But this is actually the tonal noise. And these tones here usually don't appear. They appear only in unstable conditions when I have this envelope here. No tone producer. And that comes from the feedback. Acoustic feedback, which is basically all coming from transition from TS to KH waves. That's what we explored. But many people tried, couldn't figure out. This was one of those biggest magics in fluid mechanics for many years, because nobody could understand what's going on. And you'll hear later on this. I have the recording because the experiment was done in France. I was a visiting professor at the course Central de Lyon in France, particularly working on this project. So we did all the analytics. We got the money from Air Force for that because we scared the Air Force to death. We said that, okay, the Air Force were trying to develop microwave vehicles for like surveillance, you know, spying things, right? And all of a sudden we showed that this guy can produce like huge noise. So of course it's no longer a stealth operation. So they're really scared. So they give us money, the guys investigate what to do. I mean, otherwise we'll be like, it's not gonna work. So we were doing this kind of analysis for that reason. And French were doing their experiments. So I'll show the recordings, the noise. When you go outside this envelope and you go inside, it's just crazy. We'll see that. This is all about these feedbacks. That's what I'll show here. The airfoil. So the bound relations thing is TS waves, but TS waves are slowly growing. So by themselves, TS waves would not be able to produce any kind of noise or feedback like this. It's all about the thing which people could not understand, that there must be LSB, Raman separation bubble, very close to the trailing edge. And the conditions for this noise is when this TS wave is very close to the trailing edge. Then you have transition to KH wave, which becomes really high, and then it sustains the noise. But when you go increase the angle of attack, then what happens to the LSB, to the bubble? It moves to the upstream, to the leading edge, and then after LSB, the flow immediately transitions to turbulence. And of course, turbulence cannot sustain any instabilities. So everything is gone after. So only in the condition of one LSB at some angles of attack. That's what explains this envelope. Again, I'll spend more time later on. But this envelope is all about the area where LSB is very close to the trailing edge. Okay. It's very kind of interesting thing. So this kind of mechanism was originally proposed by Longhouse. Before that, Chris Tam, if you don't know, Chris Tam is phenomenal. He's a guy, he's like 90 right now. He's still a professor in Florida State. But he's a guru. He was the one who explained the jet screech first time in the 70s. He published a paper. And so screech is basically also acoustic feedback, the same thing. But that's acoustic feedback. If you can imagine, there's a jet, there's a nozzle here, and this is like this is a jet coming from the fan, turbofan or turbojet, right? And so usually when you have this mixing layer, you have this vorticity building up here, and so the screech basically is coming when there's a vorticity, and this instability wave creates this kind of vorticity here. Eventually, they bounce back and forth, and that's what creates a screech. So he was trying to explain the same thing for the airfoil. He thought that's the thing. Published a paper in the Journal of Acoustical Society of America. Now it appears completely wrong, the paper, because we basically said it doesn't, just cannot happen. What happens is basically Longhouse, which came later and said that's the mechanism. But then it was back and forth, because Christian was saying if this TS wave, it can happen, because they cannot figure out that it's LSB. Nobody knew about that. So we were the ones who came and said that's what happened. Anyways, that was a very interesting thing. I'll be talking about this as a separate presentation. That was my favorite topic. There's so much physics there, so much interesting thing happening. And that's really amazing stuff. Now, I'll be focusing now on two projects. We still have time, which I will not be covering in future talks. So one project that was my student from Moscow Institute of Physics and Technology, came with his wife Marina, both were PhD. Came and yeah, interesting. They came, it's like 7 years ago. So they're from my school. It's my alma mater, Moscow Institute of Technology. That's why I get ready. So they came. Now it's unfortunately very difficult to bring them because of the visa restrictions on Russians. Just impossible. But they came at that time, and they worked together, but on slightly different projects. I'll talk about Marina, her project later on. Peter was pretty much doing the work for everyone, for both of them. But he was he's a genius. He actually works in a completely different area. He actually went to Purdue to work for Alexeyenko on the chemistry, chemical things for films. Yeah, something. No, he's now in pharmaceuticals somewhere because they all over the place. I thought I'm everywhere, but Alexeyenko is everywhere indeed. Like all kinds of areas of research, from chemical engineering to aerospace to mechanical, you name everything she does. And she's a department chair, Purdue, for aerospace engineering. So he worked with me on this thing, FAA research, and then he's now a chemistry guy. So see that happens. Marina is doing some kind of diesel engines in the company, which is in Indiana, by the way. You know this company, I forgot the name of it. It's very famous for diesels. It's actually probably the only one which produces now. Cummins, I think it's Cummins. Anyway, so she works there. They of course divorced. That's every couple I know in Russians, they divorce when it comes to students. I don't know, it's just some kind of bug or something. And I don't know a single one really. When I was at Notre Dame, like 60 people Russians, like zillions of couples. Not a single one. We were the very last one. Go for that. I don't know. Something is in America. It's like bug. It's like people just change tremendously. Beware of it. America changes people immensely. Anyways, so this is a project with FAA. So I was a consultant, still formerly consultant for FAA. I had this badge for this thing, and so we go to monthly meetings to Washington to report on the progress. So at that time, the idea was to integrate. It was back in the 2015, 16, 17, something like that, before COVID. So the idea was actually to integrate operations of UAVs in the terminal zone. So basically on the airports. So they thought that there will be rightly so, that there will be UAVs burning together with the big aircraft. And for instance, the big thing was actually what the separation distances are. Yeah, for them, it's a big thing. You need to establish some separation. If you have Boeing 787 or Airbus 380, and then behind there will be a small plane, UAV flying. So what's going to happen? Because there's a huge vortex system coming from the wings of this particular takeoff. And so we were trying to understand what kind of loads, loads will be on those small guys, and how you prevent, how you establish. Of course, FAA has a special program. It's all about what they call wake safety analysis. We can announce wake safety. So they have a program which actually proposes, it's automatic. You basically say, put the numbers, and it immediately tells you what should be the distance, how should be this and that. They do this it's part of the big prediction code. And we basically were integrating our analysis with this particular code. So that was our purpose. So we were coming, that time was funny because when I came to work for this group, I found that all the people there were actually like administrators. Yeah, they're all Americans, but all the work is done by Russians, actually sitting in Russia. So I think Americans were still very much should be concerned about that because everything is done over there. Anyway, so there's a lot of people who actually, because there was several of us sitting right in the in this building where they are the administrator who were in charge of this project. So it was wake safety group analysis. Anyways, so so this is what happens, right? You're all familiar with this concept, right? Assume that the wing produces induced drag because of the huge vortices at the tips of the wings, right? These huge vortices roll over, they create a wake system behind the aircraft. You'll see it all the time in the skies. Did you see that? This wake behind, right? So that's what happens. And then of course during the takeoff, it's a lot of weight, a lot of lift. The more lift, the bigger the system, right? Familiar with that? You remember the formula? Calculate what should be the induced drag. is proportional to the lift square. So you double the drag, you quadruple your drag. You double the lift, you quadruple your drag. So all these huge jumbo planes, they produce a lot, they have to carry a lot of weight, so that means they have to produce a lot of lift. They have a huge induced drag. But this induced drag is all due to huge vortices, which are coming up. So anyway, so that's what we have. And this is a part of this prediction system from FAA. That's how it looks like. So they mimic all this like weight system, and then they look. So there's a leader aircraft, one in front, and there is a follow aircraft. And so you always see where the wing interacts with the flight path of the follow aircraft. What happens when it gets into this flight path? And so we were predicting the loads from this leader aircraft on the UAVs. Could be also applied to the terminal zones. It could be during flight. You probably saw that. Did you actually ever notice when you're in a flight path of the different aircraft, you hit the wake during flight? I'm not sure how much. I fly all the time. This is my country number 99, so I flew everywhere in the world. Like in the last 2 years, twice around the world. So when you hit so it happens. It's not just turbulence. When you hit the wake of the other aircraft, which happens, you basically will be like jumping like crazy. It's like one big thing. It's not like all the time. It's like boom. You see that? I mean, that's what happens. So that's dangerous. Like this thing is okay, but this thing may be actually dangerous. But it's particularly dangerous at the takeoff because the ground is very close. If you hit this thing, you can actually still go down because you still have air down there. But if you're not, then you're in trouble. At the ground, that's how many crashes happen. For the general aircraft, with a small aircraft, when they hit the wake behind the big aircraft, just taken off, they just like some kind of thing going on and just boom, and that's it. There was many cases like that. So that was one of the biggest concerns. Of course, for FAA, that's why there was so much interest. You had some question?
Yeah, I was about to say exactly that was what happened in San Andres Island like 2 decades ago.
Yeah, that's very common problem. Yeah, the crashes at the takeoff. Yeah. Because of the wake effect, and there was a lot of investigations. Anyways, the system which the FAA calls FAA CTAR WSS Safety Investigation Toolkit. That's what it's called. Anyway, that's what they do. It's a toolkit which involves all kinds of analysis, both low, mid, and high fidelity. So the thing which we're doing on top of everything, we were like, this is like open form. You do open form, right? So we did the open form predictions. One of the things to do. So we have the system of like 2 wake vortices, right? That's what it is. And we'll look how these vortices evolve, because that's what's important. So behind this big aircraft, when it goes, it all depends. The trajectory of those wakes all depends on the surface conditions. Like for instance, if you're next to the ocean or a river, that would be the case of LaGuardia, for instance. Like everyone talks about New York, LaGuardia Airport next to the river. Oh yeah, Hudson. Right? Or if you're next to the if your airport is located next to the forest, or if you're located next to some field with like grass or anything, the trajectory will be different every time. And that needs to be accounted for the elements, that the wakes will be behaving differently every time. So depending on the particular situation, particular airport, we need to be taking care of for the terrain conditions, solid porous. So we investigated solid porous and water surfaces surrounding the evolution of this thing. So if you go this, so this is open form. For those of you doing this work, so basically we give the open form. So you do software with this library, finite volume, second order discretization, piece of simple. Volume of fluid, that's the method to account for this multi-phase system which we have between for instance, water and the surrounding, which is like the air. So the porous medium, which is basically the forest. Forest is modeled as a porous medium. So you have next to you like forest, it's porous. So there's a Darcy for Heimer source term, which is involved as a EVF, basically a wakeboard experientialization. So there's a Berkham-Halleck model, which is people use. It's interesting because we will go to the conferences. So NASA would have the turbulence research group, atmospheric turbulence research, which was basically doing the predictions what happens with the turbulence when it goes close to the different forest conditions, or etc., or with the wakes, etc. But they closed this group at NASA. And the guy was going like, he's very famous. He was like, oh, we used to walk on these things, but now like we don't walk because it goes. Anyway, so we were like for a while we're like the only ones who actually walking. on this whole area. But the FAA was interested, and of course, I would think that you would imagine the FAA should correspond much with NASA, and NASA should be corresponding much with FAA. They just hate each other, really bad. So they don't communicate. It's by the way, it happens also between different Air Force bases. I was a connector everywhere between NASA and FAA, between the Air Force Eglin and Air Force Wright-Patterson. They would not talk to each other. Work on the same program, the same names of the groups. They would ask me to basically like be mediating. I don't know. It's just some kind of like psychic. Everyone is doing their own and very, very protective what they're doing. So particularly FAA and NASA. NASA develop a lot of things. Why don't they give to FAA those packages? No. So we were developing ourselves, given to FAA, and consulting with NASA, and NASA, okay, we'll give it to you. So you understand, that's kind of strange things. All right, so comparison with experimental data so for water surfaces, we did this analysis. It was pretty good in terms of the predictions. So our analysis, there was also DLR. Oh, Germans were doing a lot of things too. So Germans, DLR, a lot of research we're doing where they will come and also like talk to us at the conference. They were still working on. NASA's not, but DLR was still working. DLR is like German. So we did LAS fine, DRL, LAS, so we were like comparing. I think we were actually better in many cases with the experiment than anyways. So that's how, as I mentioned to you, there's a lot of interaction going on. And you can see flat porous water for different conditions. You can see the evolution of these waters is totally different. Very importantly, these waters behave in a totally different way. Well, I mean, differently. So that needs to be accounted for when trying to design the operations for the UAV behind. You need to know where this water is going to. If you don't know, you just hit it and you don't know. And that's what usually happens. When the crashes happen, the pilot just doesn't know what's going on. He flies, he thought the vortex is there, but it's here. And he hits it, boom, he's done. So that's happened many times. So this kind of analysis is really important for understanding this phenomenon. What's going to happen. So you see the trajectories, position in space, circulation. Circulation also is different depending on the, the terrain. If you have vertical position, horizontal, every time it's very different. And also we involved the wake impact effect. So we did what we call roll control ratio. So that's for the guy downstream. So for the small UAV, which tries to fly behind an hopefully general aviation aircraft behind the wake. So we were for FAA was UAV, but it applies to any kind of aircraft. We had this kind of RCR ratio. That's how we actually looked. What happens if there's a UAV flying or trying to take off behind? What the impact will be. And so we looked at the Osprey. That's a small UAV Predator, big one, Global Hawk, huge. So and then in front there will be Boeing 737. So and we'll see what kind of RCR. This is a impact severity basically criteria. What happens? So the red line, you're done. So if you get there, then basically you crash right away. So you see, if you get for the Osprey, yeah, if you hit the wake, that's it. You're not going to survive. If you get the Predator, okay, you get in the yellow zone. That means that you'll be pretty much hit. If you design your flight control properly, you can still do okay, but that will be difficult. For Global Hawk, doesn't matter. I mean, it's huge, so it's not as bad. Anyway, but they're big in size. So for instance, for this guy, it's tiny. So you really have to hit the jackpot, get right into this thing. Yeah. So all this analysis, of course, apply to any kind of aircraft, or general aircraft as well. So that's why this is important. And so we did this analysis. Like this is small. This is intersection plane of this wake, and this is like your jet. Your airplane, like small UAV, anything like this. And we did the gas analysis for the far wind gas model. So FAA developed the gas model, which is typical to predict for the benchmark, predict the gas effect. So that's all includes the distance, the forward velocity, the et cetera, et cetera. So that's how you analyze. And that's usually how it looks like. It's like a big spike. That's the effect of the wake. That's right. So robust nonlinear control design, that's what this guy from physics department does. It's all about crazy theories, all this error, auxiliary regulation error, you try to minimize the error as the control design, et cetera, et cetera. And eventually we were showing that with this particular design, we were doing this control, for instance, with the synthetic jets, for instance, or you could do ailerons too. So you can actually try to do the design, which will be trying to compensate the impact of this wake on the aircraft, right? So that was the idea. All right, so that was the real aerospace. And can you imagine, that's the bonus. That's the present for you guys. How about this? That's what was my research for many years as well. I am a researcher in computational cosmetology. It was very much interesting for girls. I would go to the conferences where just the opposite. I mean, you go to engineering conference, you have 1,000 guys, 1 or 10 girls. You'll go to the cosmetology conference to present this thing, it's exactly the opposite. 10 guys, 1,000 ladies. The cosmetology doctors. Anyway, so I was involved for many years with a company called Premier Farm. It's part of what we call APG Labs. It's a New York-based company, and they were doing the girls need to listen to this very carefully. So this is basically micro injections, which you can sustain your beauty for many years. It's the micro injections in the face or any other areas, and you can actually produce the peptides which can reawaken your stem cells. Your stem cells, they go sleep up to 30, and that's why you become wrinkles and everything else, because they basically sleep. So you need to waken them up. So these peptides were developed by this company specifically to wake up the stem cells, so you become all of a sudden like a young guy. So yeah, go. Okay. Applies to everyone. So anyway, so it's new approach in skin longevity research. That's what it is. So we do these challenges, of course, but how we solve this project, I can tell you, because it was a grant between the Embry-Riddle and the company. And we were trying to advertise this as a kind of like NASA research at the same time. The idea is that people who are going to Mars, how about this? This is a NASA research. By 2035, we need to send people to Mars, right? By some estimates, on a trip to Mars, 5% of the astronauts' cells would die, and their chances of cancer would approach 100%. So for those guys going to Mars, there's almost 100% chance of skin cancer because of radiation, ionization, everything else. That's a big thing. How you protect those guys? So we thought about this. You need to sustain the stem cells properly so they can actually keep the skin young and prevent any cancer. Something. So morphology of the skin suffers great changes during space travel. Skin produces higher level of collagen, dermis is shrinking, 20% as space form. So I was really into biology. I had to learn all these things, like all of how the stem cells operate. So the idea, the company actually was trying to develop the idea, and it actually was pushed by many companies at the time when they were developing this new research on the DNA repair, particularly using this NET plus booster that was Australian research. So you can actually go from this to this. So next time you go on dating, you don't know how old is this guy. He could actually 70, but he looks like young, like he's 30. So that's what I mean. But who knows what's going to happen inside? You don't know. But on the surface, he looks like young. So that was the idea. And indeed, the research which was Premier Farm was doing with this particular stem cell kind of reawakening drugs, with the oxygen carrier. This is the most famous one, the hexapeptide 7. Then they developed this mesowartan, something else. I forgot the names of this thing, but it's basically all called mesotherapy, all these things. So you can see, like from here, you can go here, for instance, in like a couple of sessions. So there's those kind of things. So anyways, I think the president of the company should be like happy that I'm reporting it because they're always looking for the market where to sell these products. So we were doing the computationally optimized delivery of compounds into dermis. That's our big thing. So this is how the skin cells look like. If you look at the skin, that's how it's all divided into many parts. But basically, it's dermis, epidermis, all the steps. And so, and you have this, of course, this is your hair and stuff like that. And it's very complicated in general. How do you actually do the simulation? How things propagate through these kind of layers? It's not trivial at all because it's very complicated structures. You have to account for a lot of things. If you do it at a molecular level, forget it. It just takes forever. So we had to do some sort of averaged analysis. So this epidemic, so it's late, you can see here. And we have to appoint some kind of particular coefficients, like diffusion, metabolism coefficient, clearance coefficient, all kinds of things like that to count how much of this, for instance, of the stuff goes into the bloodstream, how much retains, how much converts. So metabolism basically has effect as well. on those things. So all these components are there. And also your actual cells inside, they could be either like attracting like water or they could be attracting the fat, or like fat could be rejected by some passes, and water can be the same way. So it's could be different. So you have to account for all these things, like lipid pathways here, and so on. So you have to account for this. So we did this research, this called analysis, right? So we have the diffusion process, we have the diffusion, partition, binding, metabolism, all these processes that physically happen at the level of the cells, skin cells, need to be accounted for. And they count for a lot of experiments which people are running. Actually, dermatologists are like scientists who are like the lady who was doing the research was actually she's a professor in San Francisco University. She's doing the dermatology research, also skin cancer research, all these things. So she's doing a lot of analysis. Particular analysis was actually to see if those peptides which were injected will not produce any cancer. That was a big thing because they produce effects on the stem cells, but what this chain of events may produce in the end, it could actually produce cancer. So they're trying to avoid this, but they actually. So she was doing a lot of research to analyze this thing, and she found no, because there's very different routes, like different pathways, how these things can develop. And she found that this particular pathway with this treatment does not produce this cancer. So that was a big thing, because everyone would be concerned, first of all, right? You don't want to be like young, but then directly. There's some bad things. So the point we were trying to do, for instance, for the micro injection, like micro needles here, versus like our injection with a single needle, we put everything in the dermis because, for instance, these peptides are very heavy in molecular weight. So those heavy molecular weight peptides will not be able to penetrate through this like dermis layer, right? Or stratum corneum, which is on top. It's just impossible to get through because they're too heavy. It's not difficult to diffuse for them through. So you have to do the injections, penetrate this thing, and then release it right there. Then they go around and basically rejuvenate your dermis, an epidermis by this. So that was the idea. This is the equation we solve. Computational pharmacokinetic model, CPK. So that's where you go to these conferences. You basically, it's an area of research, CPK, computational pharmacokinetic. And we basically solve this sophisticated diffusion equation with a bunch of things, which relates to the C is the concentration of the actual compound inside. CB is which is unbound, and there is a bound, which is bound is when it's blood. It's what's called compartmental model, because you have everything is in compartments in this case. And you solve these equations, which account for the binding, unbinding coefficient, metabolic coefficient, eliminating coefficients, all these things, which accounts for the blood elimination, the metabolism, and everything. You solve this, and what we did actually, we used a very interesting method, which is meshless. You don't have to put any kind of mesh inside. There's no grid. It's a meshless method, very new. Well, rather new. It's a transient solution. Basically, it's kind of like spectrum. It's kind of spectral, but it's a bit more efficient than spectral. Spectrum may take forever. This is more like a sparse spectrum. Those kind of things. So this is actually the time marching process where you estimate at each next moment of time what happens with your concentrations based on like a simple error scheme now. So we found this kind of analysis, produces us distribution of this stuff through all these layers, and eventually we could predict these movies. What happens when verapamil is like a benchmark, like a regular drug which people put for I don't remember which kind of disease, but this, for instance, could be some other. This is one of those peptides. When you put and you can investigate how far it goes. So what's the research is producing for me? It's the guidelines for the cosmetologists, for the ladies who do usually ladies, small knowledge doctor who do the injections, how often they should be done, what is it, how deep, how often, how much they need to inject. So that will be covering the entire area. So that's basically the optimization done for these people talks. So that's the idea. And eventually we're doing this TDD, it's transdermal drug delivery, TDD. Model predictions, and we predicted for different types of compounds, what happens, how they develop after 4 hours, after 8 hours after injection. So you can have this kind of predictions. So people know what the effect is so much. Yeah, so we'll grab it. And that's it. Thank you for your attention. I'm pretty much in time. This is a group again some years ago. I'll show you every time different pictures. Thank you. Thank you guys very much.
We're open to questions.
It's a bit of a shock.
I have to.
Absolutely.
Okay, no, go ahead. Jonathan. Interesting.
Okay, thanks. Thank you for your presentation, Professor Golubev. So I have two questions. The first one is for the size of this wind vortex. How many meters are we talking about? I ask for that because today in Bogota, our capital, we have a distance for two airplanes of 1,200 meters. Practically is a collision. So the wind vortex effects are about how many meters? And my second question is for this skin treatment, how can we apply nanotechnology for the injections and diffusion in this case?
Okay. The second question is, I have no idea. Nanotechnology, you're developing nanotechnology. I understand it's really like leading a cutting edge thing. So you have to show me what you can do with this. Then I can say if it's actually will be applicable or not. Okay, so for this particular research. For the first one, it's easy. I can say one thing, it all depends. If you look at the that's why these programs are developed by FAA. It all depends on the aircraft weight for the guy in front of you. A380 is in one category, separate one from every one of them. 380, the heaviest one, is kind of separate category. Whole bunch of them, like Boeing 737, Airbus 321 or something. Others, they have a second category. And then there's a small planes, and there's many categories. And they all define the weight, and they all define the distance, separation distance. But this separation distance, again, it's a classical for the specific type of aircraft we usually operate. Like, it all depends, again, on the weight and size of the aircraft behind. So for UAV, there was like totally different thing, for small ones. Because, so that's why we're coming here to say, okay, your separation distance guideline should be changed. So it should be like, instead of like 500 meters, maybe 1,000 or something like that. So it all depends. So this program allows to account for all these factors. See,
Thank you. Okay, thank you. Before this question, the coffee break is ready. So I will just ask this question and then go.
yeah, sure.
Coffee break. It's just more like kind of a rhetorical question, but does it make sense to have like CFD research in a school without HPC?
I would say you have other options now. You have the cloud computing. Have you talked with Amazon?
Yeah.
They have Amazon has cloud computing systems, so they can allow to run your simulations on the system. You have to pay. So that's the thing. If the university provides the budget and for this thing, but they don't want to invest in the HPC their own, you can use that. But you have to persuade them that we need this. The second thing is you have to get involved with the big agencies like we do at NASA research. They provide us access to the NASA computer system, HPC. So we do most of the things on the NASA HPC. What we do in SF research, they have some cluster. What we do not DoD, Department of Defense. For instance, this Navy research is all done on DoD clusters. So we use that outside. I would say that actually it used to be that most of the stuff was done on the Embry-Riddle, like Vega. These days, all the projects, which pretty much majority, are done on some other things. Because I only have one lady, Aliyah is my student from Kazakhstan, who's not covered by the grants. She's doing like some other things. I'm going to show it next time. And so we have to use the university. Other than that, everyone is doing NASA or DoD, right? I said.
Sí, ya está el referido listo, por favor. Y si alguien tiene alguna pregunta en español, hágala sin problema, por favor. Ya sea Juan Carlos o no lo puede traducir. Por eso, gracias. Profesor, no.
Yeah, you want to plug?
Thanks, Professor, for your presentation. I want to know what's the relationship between the ROTC program, the US Air Force, and the Embry-Riddle University.
Yeah, I have,
So I'm so interested in becoming a US Air Force pilot. So I want to know how this university can help me to follow this path.
You go for free if you are part of the RTC, but then I'm not sure how to get enrolled in RTC, because I thought you need to be like at least a resident or a citizen. I mean, they don't take anyone, I don't think so. But we have a lot of RTC. Usually in my class, I have at least 5, 6 guys in military uniform all the time. And you use RTC people come and get it to the folks. So we have a lot. I mean, how it works. But I know some people, actually, I know some Russian lady became RTC. She would come, So I think she became a permanent resident first. Still, her parents came, but she was like a young girl, and she became enrolled in RTC.
Gracias. Pues, mucho podemos ver y ahorita regresamos.
Sí, lo que te gusta,
todo lo que me
boticos.
gusta,
Todas las boticas.
todas las boticas que me gustan a mí.
Okay,
Professor,
Can I ask you a quick question?
yeah, quick, because I want to go. I have only 5 minutes left before the next presentation.
yeah,